Good afternoon, dear colleagues. My name is Feciskanin, and I would like to present our work with Professor Mina and optimization of triangular network and its use in DEM generalization for the lens surface segmentation. The presentation contains the result of the latest experiment published in Transaction in GIS. The issues of surface segmentation and the concept of elementary forms have a strong background in our department. Therefore, we are dealing with generalization in a wide range of scales, and the generalization results significantly affect the generalization results. And we are facing the problem of the quality of generalization methods. We have found that they are generally insufficient to preserve the shapes of the landscape.
Richard, can you please try and raise the volume?
Is it better now?
I think so.
Okay. So, DEM models or polyhedral representations of the lens.
Richard, hlasnejšie, slabo je ťa počuť.
Yeah, I know, but I'm not sure how to increase more the volume.
Maybe go closer to the microphone.
Okay, it's better now.
Oh, that's much better. Thank you.
Oh, okay. Okay, sorry. So again, starting from this place, that DEM models or polyhedral representation of land surface are effective in capturing the shapes, especially in places with significant shape changes. The structure is also suitable for creating various simplified versions, so it can be used for generalization. The question is how to use these benefits to create the best possible simplified model. The grid-based methods predominate in the land surface generalization. Also, many generalization methods use DEM-based DEM. Here, a common approach is to extract 3D points from the DEM and use them to reconstruct the terrain surface using DEM. Instead, the polygonal simplification methods operate directly on the triangular model and do not use the pre-processing with other structures, as is common in land surface specific methods. They try to maintain overall shape fidelity, and some of them are really successful, as we see. They are generally less controlled by subjective choices. Thanks to the optimization of the shape of the triangles, maintaining the characteristic shape of the land surface while simplifying the model led to placement of triangle edges in the position with the greatest surface changes. In contrast, the area of triangle represents the relatively homogeneous part of the surface. This is in line with the principle of maximizing internal homogeneity and external heterogeneity in a lens surface segmentation and the concept of elementary forms. We choose quadratic error metric simplification method as one of the polygonal simplification methods whose optimization conditions are in accordance with the characteristic of the optimal triangle. In a short, that is triangle which is long in the direction of minimum value of second directional derivative and narrow in the direction of the maximum value of second directional derivative. This method was developed primarily for computer graphics. However, it's universal and suitable for use in land surface modeling too. It's one of the decimation methods that use the edge contraction procedure to simplify the model geometry. An example of one contraction step in 2 dimensions is shown in the figure. The location of new vertex V is at the smallest quadratic distance from the planes of triangles with vertices V0 and V1. Here are the examples of generalization results. The models of one testing area, Hills, Slovinec, and Sandberg. We created almost 100 different levels of generalization from initial LiDAR data model. These are models consisting of 100,000, 5,650, and 100 triangles. The ability of the algorithm to capture the most important features of morphology with a very small number of triangles is evident here. Widespread approach to generalization in land surface modeling is a procedure based on the maximum Z tolerance method. It's implemented in various GIS software. This method is controlling the maximum elevation difference between each point of the original DEM and the thin surface generated by the significant point set. To compare accuracy, we generalized all input models also by the maximum Z tolerance method to similar levels as by the quadratic error matrix simplification method. For each generalized model was represented by a set of randomly generated points located on the triangle planes. For each point, we computed the signed Euclidean distances to the corresponding initial model and calculate the summary RMSE. Here are the comparisons of the summary RMSE. This is the second research area, Dolina Zeleného Plesa Valley. In model consisting of the same number of vertices, RMSE of quadratic error matrix simplification is much lower. These are graphs for the model of artificial mathematical surface. Here the RMSE of quadratic error matrix simplification and is several times lower, as you can see. Overall, the chosen methods achieve significantly better accuracy results than the maximum Z tolerance method in both artificial and natural surfaces. The affinity to constant value of first and second order morphometric variables is indicated by the concentration of third order variables, changes of curvature around 0. This can reveal the suitability of triangular network for land surface segmentation. The values of these 4 changing of profile and tangential curvatures were calculated based on the third order polynomial least square fitting over generalized thin. The quantile-based measure of kurtosis, K0, was used as numerical expression of the concentration data around 0. Here, in the numerator, 25th and 5th percentiles representing the spread of the set disregarding extreme values. In the denominator, there are 5th percentiles on the right and on the left from the 0 value, respectively. This is the result of the analysis of model of Slovinec-Sandberg. You can see on the graph the values of K0 for each curvature and their average. Figure A is very similar to initial model and captures even very subtle inhomogeneous features such as particular borders, generalization towards the level of figure B, smooth out these smallest features, but retains the bigger features clearly compounded from elementary forms such as gullies and anthropogenic terraces. The model with the maximum value of K0 is shown in figure C. These generalize gullies and terraces, but preserve bigger high-order landforms such as fold and erosional scarps or planation and structural surfaces. The next steep decline in K0 to the level of 100 triangles in figure D represents losing information about these elementary forms. Here you see the comprehensive comparison of K0 values of curvature changes in 3 areas of the Dolina Zeleného Plesa Valley. Figure A, with the maximum of K0 from the bottom graph, shows a slightly generalized model. This covers all small gravity, glacial, and fluvial landforms, such as bigger creases and rock faces, debris slopes, moraines, and river terraces, but generalized individual irregular borders, the smallest gravity and erosional features, and possible DEM errors. The model in figure B, with the local maximum of K0, catches well only the biggest glacial, fluvial, and tectonic landforms, such as glacial cirque and valley and fault slopes. The medium subset of the territory at the upper part of the valley in figure C and D generally reproduce these pictures. The K0 curves are naturally modified when catching smaller subsets of the valley. In a small territory, the bottom of the glacial cirque, the K0 curve has maximum in the most detailed DEM in figure E that reveals very subtle features, mainly drainage of small ravines dissecting the cones. This is probably because the ravines are extremely dense in this small territory and they are compounding from the homogeneous elementary forms. The principal difference between the natural and artificial surfaces is prominent when comparing the averages of K0 values in this figure. On the scale of natural surfaces, the K0 values of the artificial surface are practically constant. The markedly linear course generally points to the missing signal of elementary forms. On the contrary, variation in K0 of natural surfaces carries a signal about the affinity of landforms of various hierarchical levels to elementary forms. The quadratic error metric simplification algorithm preserves important topographic features very efficiently, including the high-level generalization. We tested the hypothesis that quanta-based measure of kurtosis of changes in curvature can indicate the suitability of DEM generalization for elementary land surface segmentation in 2 various territories and 3 various details. Generalizations corresponding to the local maximum of K0 depict well the leading landforms in nested hierarchy. The experiment of comparing K0 values of generalized natural and artificial DEM shows significant differences between natural and artificial surfaces, which can easily be interpreted in terms of theory of elementary forms. So that's all. Thank you for paying attention. See our paper for more information, or you can contact us on our email addresses.